So let me ask you this. Do you believe a clock always runs at the same speed no matter where you are on Earth?
I mean, that's the assumption, right?
It has to be. We rely on it for everything. Global time synchronization for, air traffic, setting our morning alarms.
It's what we live by. That time is this fixed, universal constant that ticks the same for everybody.
Mhm.
The comforting idea.
But it's wrong. What if I told you that if you're standing here right now and your friend is hiking, say, thousands of feet up in the mountains, your personal timeline isn't actually running parallel to theirs?
And that's not a hypothetical, that's a measurable fact. The assumption is fundamentally wrong.
Welcome to the Deep Dive. Today, we're looking at a stack of sources that confirms one of the most counterintuitive discoveries in modern physics. Time does not move at the same rate everywhere.
It's true. Your physical location, specifically the gravitational pull right under your feet,
Yeah.
it directly affects the speed of your own personal timeline.
So our mission today is to really get into how gravity influences the fundamental flow of time and, why this is so critical for the technology we use every single day.
Exactly. We're moving beyond the textbook definition of time as this absolute rigid drumbeat. It's more like a variable rhythm.
And that rhythm is governed by mass and gravity.
You got it. This deep dive is into confirmed physics that honestly feels like pure science fiction.
Okay, so let's unpack this core discovery. Scientists have actually measured this, right? This isn't just a theory.
Oh, absolutely. They've successfully measured this minute difference, and they've found that the higher you go above sea level, the slower time actually moves,
Slower, relative to what?
relative to time passing for someone down at sea level.
So that completely upends the old assumption that time is fixed,
It does. It proves it's inaccurate. Think of it this way. Earth's mass creates a gravitational field.
right?
The stronger that field, the more time gets distorted, the more energy it takes for time to move forward. So time passes at a variable rate.
Okay, so the closer you are to a strong gravitational source, like the center of the Earth, your clock runs. Wait, faster or slower?
This is the key part. It runs faster compared to someone who is further away.
See, that's the opposite of what my intuition says. I always associate strong gravity, like with black holes with time stopping entirely.
And that's a fair assumption, but here on Earth, it's all about the relative difference. The closer you are to the mass, the faster you age relative to the person higher up.
So we have to be really clear on this. It's always a
It's
comparison.
precisely. It's always relative. You take two locations, and time will run faster for the observer who's in the stronger gravity.
Let's make this real then. One of our sources uses a great thought experiment. Let's say you have two people. They both live for the exact same number of years, say 80 years,
Okay.
but one of them lives their entire life on a peak of a very high mountain, and the other one lives their whole life in a coastal city right at sea level.
Mhm.
After 80 years, one of them would be measurably older than the other.
Yes. The person living at sea level, the one who spent 80 years closer to the maximum gravitational pull of the Earth, would have experienced time passing just a little bit faster.
So their personal clock would have accumulated more ticks.
Exactly. It might only be a fraction of a second more, but it would be a real quantifiable difference. They would have aged slightly more than their friend up on the mountain.
That is fascinating. So if the result is a measurable difference in aging, however fuel, what is the physics behind it? What do we call this?
The term for it is gravitational time dilation.
Time dilation.
And to really get why this happens, we have to talk about general relativity, Einstein's description of how gravity actually works.
So this isn't Newton's apple falling from a tree gravity.
Not at all. Einstein didn't see gravity as a force in the traditional sense. He saw it as the curvature of space-time.
Space-time. The idea that space and time are fundamentally linked. They're part of the same fabric.
Yes, and that's where it gets really interesting. Because you're not visualizing gravity as a pull anymore. You're visualizing it as a topography, a landscape.
Okay, so how does that work?
Imagine space-time is like a huge flexible rubber sheet, a bit like a trampoline.
Right.
Now, if you place a heavy object, like a bowling ball, representing the Earth, onto that sheet, what happens?
It creates a dip, a curve in the sheet.
Exactly. It creates a depression. We call that a gravitational well. And anything that travels near that mass, from a satellite to a beam of light, has to navigate that curved space.
And since you said time is inseparable from space in this model, like time itself must follow that curve.
Now you've got it. That's the key insight. The fundamental movement of time clocks, aging, everything, is slowed down when it is deeper in that gravitational well.
Wait, I think you said faster before. Let's get this.
Good catch. Let me clarify. It's about the relative rate. The person at sea level is deeper in the well. The person on the mountain is higher up in a shallower part of the well. Weirdly, time for the person deeper in the well actually runs faster relative to the person higher up, where the curvature is shallower.
That is so counterintuitive. So deeper in the well, closer to the mass, means time moves faster, higher up, farther away. Time moves slower in comparison.
Yes. Think of it like a river. The massive object creates a current in space-time. The deeper you are in that current, the faster the stream of time flows around you.
And the higher up you go, the shallower the current is, and the slower your stream of time moves relative to the person down below.
That's the perfect way to put it. And this difference in gravity, this difference in the depth of the well, is the driver.
So every time I climb a flight of stairs or take an elevator, I'm slightly changing the speed of my personal clock.
You are. You're changing your position in this gravitational topography. The further you are from the Earth's mass, the weaker the gravitational field, and the slower your personal timeline advances compared to someone on the ground floor.
And the sources confirm this is not just theory.
Not at all. It's been measured with incredible precision.
Which brings up the big practical question. If this effect is real, if I'm measurably aging differently than a mountain climber, why don't we feel it? Why don't I feel a shift when I go from my basement to the roof?
Because the magnitude is, well, it's almost comically small for us humans. The difference is absolutely too small to be felt.
What are we talking about here?
One of the sources states that if you move up by just 1 meter, your clock speeds up by about 1 nanosecond every 3 centuries.
Well, 1 nanosecond. Over 300 years. For moving up 1 meter.
Yeah. It's minuscule.
But the fact that scientists can even measure that is what's so profound.
It is. And that's what moves this concept from being, a philosophical curiosity to being mandatory engineering.
What do you mean by that?
Well, despite being imperceptible to us, this phenomenon is absolutely critical for some of the most advanced technology we use every single day.
You're talking about GPS.
I'm talking about the Global Positioning System,
Yeah.
GPS.
This is where the physics really hits the road then. If the differences are that small, why does an organization like NASA have to worry about it for GPS satellites?
Because the level of precision needed for GPS is just staggering. Your phone's GPS receiver needs signals from at least 4 different satellites at the same time to figure out where you are.
Right, it triangulates, or I guess quadrangulates your position.
Exactly. And if the clocks on those satellites are out of sync by even a tiny amount, we're talking nanoseconds, your calculated location will be off by kilometers.
Wow. Okay, so the GPS satellites, they're orbiting thousands of miles above the Earth. They're experiencing a much weaker gravitational pull than we are.
Much weaker. So based on what we've been discussing, what does that mean for their clocks?
It means their clock should be running faster relative to us on the surface.
Exactly. But engineers have to account for 2 separate and opposing relativistic effects.
Oh, it gets more complicated.
A little. First, you have the gravitational time dilation we just discussed. Because the satellites are far from Earth's mass, gravity is weaker, and their clocks run faster. This adds about 45,000 nanoseconds of error every single day.
45,000 nanoseconds a day? That's a huge error. GPS would be useless in minutes if they didn't fix that.
Totally useless. But then there's a second effect. It's called velocity time dilation.
From special relativity.
You got it. Because the satellites are moving incredibly fast, thousands of kilometers an hour, that sheer speed causes time for them to slow down.
Wait, so their high altitude makes their time run faster, but their high speed makes their time run slower.
Precisely. The effects are fighting each other. The velocity effect subtracts about 7,000 nanoseconds of error per day.
Okay, so you have a 45,000 nanosecond gain from gravity and a 7,000 nanosecond loss from speed.
And when you do the math, the net result is that the clocks on GPS satellites run faster than ground clocks by about 38,000 nanoseconds every 24 hours.
And they can't just let that drift happen.
No way. They have to adjust the frequency of the satellite clocks before they even launch them. They are built to tick slightly slower on Earth, so that when they get into orbit, they tick at the right speed to match us.
That is the ultimate aha moment. This isn't some abstract physics that only happens near a black hole.
Not at all.
This is a mandatory calculation for the traffic directions and food delivery we use every single day. The technology has to literally pre-age its clocks to stay in sync with us.
It's the ultimate confirmation that time is fundamentally intertwined with the geometry of the universe. The simple geometry of where you stand is a constant, subtle factor in determining the speed of your life.
And that brings us back to what our source material was hinting at, the
Mm.
more philosophical side of this. We all walk around assuming we share the exact same present moment, the same clock speed, but that's not strictly true.
No. Every time you move, you're subtly changing the rate at which you proceed through existence relative to everybody else.
It connects time, this huge abstract concept, to something so concrete, the geography right under our feet.
It really does. The idea of a fair or equal time for everyone is just an illusion of our perception.
So, to summarize what we've uncovered in this deep dive, time is not uniform, it's not a constant. The greater the density of gravity beneath your feet, the faster your personal clock runs compared to someone where gravity is weaker.
And this phenomenon, gravitational time dilation, isn't just theory. It's a fundamental truth confirmed by advanced technology like GPS, which has to account for these tiny differences just to function.
Which leaves us with a pretty big question for you to think about.
And it's this. If time is constantly changing based on your altitude and your speed, even if it's just by nanoseconds, what does that really mean for how we define a constant universal now?
Right. If my now is running a fraction faster than yours because I'm standing closer to the ocean,
How fundamentally connected is our personal timeline to the simple geography of where we choose to stand? It turns the very concept of a shared moment into a verifiable matter of, well, real estate